Okay, so thanks for giving me the opportunity to close this session by talking about the future quality in China. So I'm Mingwei Li from MIT, and this work is also in collaboration with the Tsinghua MIT China Energy and Climate Project. So I'd like to start my talk by introducing the recently announced energy policies in China. So last year, China issued the action plan on air pollution control. Although this plan is specific for air pollution, it also has some energy policies. So the primary target is to cut the energy intensity by 20% in the following 5 years. For those of you who are unfamiliar with energy intensity, it is defined as the energy consumption per GDP, and China has experienced a long-term reduction in the energy intensity over the past 3 decades. And a more recent one, which also attracts a lot of attention, is the US-China climate deal. China has pledged to have its CO2 emissions peaked in 2030. So in this study, we will assess the effects of and the co-benefits of these energy policies on the air quality over both China and the US in 2030. So to achieve this, we coupled an energy economic model and an atmospheric chemistry model. The energy economic model we use is called CRAM, and this is developed by the Tsinghua MIT China project. And this model has global coverage, and also aggregates China into 30 provinces. And the base year of this model is 2010, and it will make projections thereafter through 2030. And by using the energy consumption output from the CRAM model, we then scale the risk inventory by province and by sector to get the projections for the future anthropogenic emissions. And for the future emission factors, we assume an exponential decay. And then we use the JuiceCam model to simulate the ozone and the PM concentrations. Here, we did not consider the effects of climate change, so we used the same math fields for our future runs. And further, we will also quantify the health impact of these energy policies, but this part is not covered in today's talk. So we have 2 energy scenarios. The first one is a business as usual, and second one is a policy scenario which has a constraint on the energy intensity, which is based on the action plan. So the left figure here shows the projection of the energy intensity. The black line shows the business as usual case, and the red line shows the policy scenario. Here we can see that the policy scenario has a faster reduction in the energy intensity over time, and the red figure here shows the total energy consumption over time, and the policy scenario has a slower increase. And this is because that in the policy scenario, the economic structure changes, which will favor the projection from less energy-intensive sectors, and also it will encourage the fuel switching from fossil fuel to non-fossil fuel, such as wind and hydropower. And to give you an idea what our policy scenario compare with the Chinese newest commitment, here we also show the CO2 emissions from our model. And again, the red lines for the business, for the policy scenario, and in our policy scenario, the CO2 emissions peaked in 2025. So our policy scenario also achieved the China's newest commitment and a bit beforehand. And then this figure indicates the future Chinese anthropogenic emissions for these 5 species. By comparing the business as usual and the policy scenario, as expected, we can see that the policy scenario substantially reduced the emissions from fossil fuel combustions. So for species like SO2 and NOx, which has a large share from the fossil fuel combustion, the policy scenario has a large difference from the BAU case. But for species like ammonium, which primarily comes from the agriculture, the policy scenario does not differ much from the BAU scenario. And this is also the case for VOC, which has a large share from the industry process. And I want to remind you that for the emission factors, we assume exponential decay for both scenarios. And basically, it's a 50% reduction over 20 years, which is the time interval of our prediction. And if we look at the trend over time and the policy scenario, all these species, except for SO2, will increase in 2030 compared to 2010. And for SO2, it's more like a flat trend. Then what's the implication for the air quality in 2030 over both China and the US? Here we assess the air quality in terms of both PM2.5 and also ozone. And here the first figure shows the annual average PM2.5 in 2010, which is base year, and the second figure shows the difference between 2030 and 2010 in our policy scenario. And I want to remind you that the difference is only due to the changes in Chinese anthropogenic emissions. We did not account for the climate change. And so basically over East China, there is a 10% increase. And over the US, the difference is much smaller, less than 0.05. And the larger enhancement is over the eastern US. And this is because the elevated oxidants such as OH and H2O2 due to the increase in CO and NOx emissions, which will enhance the oxidation from SO2 to sulfate, from NOx to nitrate over the eastern US. And we further found that the elevated PM2.5 over the East China is mainly due to the increase in ammonium emissions. Here we did a sensitivity simulation, which we set the ammonium emissions constant at the 2010 level and let the other emissions follow the 2030 trend. And we found that the increase of PM2.5 over East China reduced to 0.3%. And the ammonium emissions is mainly driven by the population growth in China. So in terms of ozone, here I show the summertime daily maximum 8-hour ozone. And again, the first figure shows the baseline concentrations and, in 2010, and the second figure shows the difference between 2030 and 2010. Here we found that over East China, there is an 8% increase, and this is due to both the increase in VOC and the NOx emissions. And over the US, the increase reached from 0.1 to 0.5 ppb, and this is through both the increase in direct transport of ozone and also through the increase of pan formation. And lastly, I want to remind you that there is a significant air quality co-benefits in 2030, and this is defined as the difference between the policy scenario and the BAU scenario. And basically, for PM2.5 over East China is 20 microgram per cubic meter reduction, and over US is 0.1. And for ozone, there is also large reduction in both China and the US. And we will further quantify the health and economic effects from the energy policy and compare with its policy cost. So to wrap up, I would like to summarize the policy implications from our research. First, so with the energy and moderate end of pipe policies, the air quality in China will probably worse off in 2030 compared to 2010. And we further found that the elevated PM2.5 in China is mainly driven by the ammonium emissions, which is in response to the population growth. And we also found that the increase in PM2.5 and ozone concentration over China due to the Chinese exoplanet emissions in our policy scenario are not negligible. And lastly, the energy policy contributes significant air quality co-benefits over China and the US in 2030. Okay, so thanks for your attention, and I'm happy to take any questions at this point.
Plenty of time. Questions? Yes.
So, do you consider trade in your policy models? Because it seems like ammonia plays an important role here, and as China gets richer and richer, China may import a lot of agricultural products from other countries. So, the ammonia emission may not increase that amount, like probably millions of populations. So, have you considered that?
Okay, so the question is about ammonium emissions. So actually, we do consider the trade in our energy economic model, and but yes, we found a large increase in the ammonium emissions in our model, even though we consider the trade.
I have a question.
Yeah.
I know your work strongly depends on the assumption in the scenario.
Right.
I'm interested that you show that with the energy policy in place, I mean, for future, that the PM2.5 will increase by 10%. But our target for 2017 will reduce by, so that seems contradict with our, so.
Right. Yes. So, yeah, this is really a good question. So in the action plan, they actually have some end-of-pipe policy. So for those policy, we do not include it in our work now. So we only assume an exponential decay. And there's some study that they actually implicate these end-of-pipe policy in model, and they found there is a decrease in PM2.5 like by 10%. So here I just say we have a moderate end-of-pipe policy, so our policy may not be that aggressive, yeah. But the focus of this study is on the energy policy.